Hello everyone, welcome to Coders Camp. We are at 28th day of January LeetCode challenge, and the problem we are going to cover in this video is design, add and search words data structure. So here the problem statement asks us to design three methods or a class word dictionary which has three methods. The first method is to define the data structure, and the second method is to add a word to the data structure, and the other method is to search a word in the data structure. So if you look at the problem statement, the first thing that strike or stuck your mind would be having a set as a data structure, because it is easy to add a string and search for the string using a contains word and maintaining it as well. So there are two drawbacks by using set. First one is our test cases. Our test cases are not only searching for any word but also words with dots. So we have to search for words with regular expressions or something pattern matching. So if a word is having dot ad, then you have to look for a word that has any first character, but then the other two characters must match. And same goes with the other word. So we can't achieve that in a set, or it is bit complex when using a set. So what would be the efficient data structure to do this? So as the problem statement require us to process the given input words character by character, we need an efficient data structure that stores the word and search them and help us to search character by character, which is very clearly try data structure. So which is not something really new to us. We have used it already in our coding videos to construct dictionaries and find and search words. So those of you who haven't worked in try, which is pretty simple, we are going to see how it is going to work. And as we all know, that is a really nice data structure to work and play with words. Before getting into the actual implementation of it, let's understand the concept and how we are going to solve this problem using try. So try is nothing but a simple data structure that helps us to store the words which are having common prefixes. For example, here the examples given are blue. So let's start by having the root node. From root node, the first character we see is B. So from B, it is going to be a tree structure. Okay, we have constructed the first word. The second word given here is band. So we are going to insert band to our data structure. The first thing we are going to notice is B already present. Yes, B is the first child which is already present. So which is already been there in the tree. So we have to look for the next character A. Is B's immediate child is A? No. So we have to create a node that inserts A and store it. So the next character is N. So from N we are going to from A we are going to store N, and then from N the next character is going to be D. So moving forward to our next word, which is mad. So we are going to look for M in the tree. So M is not there. So we are going to insert that as a root node from our immediate child of a root. So the next character is A. M is not filled with A. So we are going to fill A next to M. And then the next character in mad is D. So we are going to fill D. So going to our final word, which is max. So max is having the first character M, which is already there in a tree as the very first character. The second character is A. The immediate character to M is A, that is also present. The next character or the last character is X. So we are going to insert X here. So this actually constructs the word mad and max, right? So this is how the insertion operation works. That is, we are going to look for the prefixes and join them as a right or a left subtree. So now how it will be useful for us to search a word. Consider we are going to search for the word mad. So now what our algorithm is going to look is its first character. So first character is M. It is going to look for the first character in the immediate child of the root. So it is present. So the second character is A. We are going to look for the immediate child of M, whether A is present or not. Yes, A is present. And the next character is D. We have two options or two nodes after A. So if any of one is D, then we can return true. So yes, there is D as well. So this is going to be true in the search function. So now consider another word, which is ban. So as usual, our algorithm is going to search for B. So in B is there, and the next character is N is there, and the next A is there, the next character is N is also there. But can we return true to this? No, because this is not the word that is given in our input. We have given only band, not ban. So in this data structure, how do we identify that is the end of the word? So to identify the end of the word, because we can simply we have the word band in our data structure, but that is not the actual word given in the input. So to indicate that, we are going to have a marker to with each node that says whether that is the end of the word or not. So with, let's say we have the variable as is word or is end of word, however you want to. So let me in short form write it as IW. So with every node, we are going to have a Boolean value that says whether it is a word or not. If it is a word, then it is going to put a Y. If not, it is going to put a false. So for every word, it is going to be a false. Only end of the words are going to have true. Same way, D and X are going to have true. All other words in the data structure are going to have false. So by this, we are going to identify whether that is the end of the word or not. So every time we are going to search for a word, our data structure is going to look for the characters, and by the end, when it finds the last character, it is also going to check is word is true. If this also satisfies, then only it is going to return true. If not, it is going to return false. So this is a simpler concept of this data structure. And there is another criteria that we want to cover, which is pattern matching. For example, let's say the example is MA dot. So let's insert one more word. Consider we have one more word, MARS, Mars. We have already M and A. I have included R and S, and its end of word S is going to have T. And there is one more word, cat. So let me insert it somewhere here. C is the first word, A is the second character, and T is the third character, and which is having T as its last pattern matching. Other things are having false. Okay, now let's see the example MA dot. So in this case, our algorithm is going to look for M first. Yes, M is there. A next, A is also there. So there is one dot. So we have to have one more character as child of A, which is also having is word is true. Why? Because we have only three characters, and the next character we find in next to A must have T. So let's look at the algorithm. We have three possible characters, which is D, mad, R in Mars, and X, which is also end of max. So in this case, we have end our search in D itself, because we have one more character, whatever character may be, and that is having is word is equal to true. So we can directly return true. So this is similar to other pattern matching, which is dot D or dot AD. So in this case, first character itself is dot. So our algorithm is going to look for all the possible characters in the root node, and from there it is going to proceed. So this dot can be C, this dot can be B, and this dot can be M as well. So we have all three choices. So we are going to traverse in all paths that is possible. So the second character is A. So from these three choices, we are going to pick the way which is having A as its next character. So if you see, we have A in cat, A in band, and A in mad, max, Mars, and everything. We have three choices now. So the next character is D. So we have only three characters. Now our algorithm is actually going to look for a D, which is an immediate child of A, which is also having is word is equal to true. So in this case, first option is cat. So we have dot A, and the third character is D, which is not matching our AD. So this is not going to be the path we are looking for, which is a false. So the next A we saw is in band. So we have A, the next character is N, which is not matching D, so we are going to skip it. So then comes MA. So we have again three choices, which is D, R, and X. So in this case, let's leave D first and go for the example R. So if you see, then character R doesn't match D, so we are skipping it. Here the character X doesn't match D, so we are skipping it. Here we have D and also T. So in this case, we are going to return true. For example, if there is another word exist which is having M, A, D, E, made. So in this case, we have matched D with the first case, mad, as well as the third case, made. So they both have the prefix mad and mad, but here E is having end of the word true, but D is not. In this case, this case again becomes invalid, and this case is the true case, and we are going to return true. So hope we made some sense with this. This is the overall logic we are going to implement in our code, but this is a bit clumsy. How actually, in which way we are going to implement it? Let's see. So here are the three given methods. The first method is to define our data structure. So how are we going to implement our try in algorithm? So usually try will be implemented using character array. So again, we are going to have a character array of size 26. So each position or each index is going to represent an alphabet A to Z. So as I said, first root node is going to start with having 26 index starting from 0 to 25, where we are going to place the characters, so which are the first characters of the word. From each word, again they are going to have 26 characters to its children. So each character is having an array of size 26. Let's see the same example we have taken: bad, max, and mad. So here the first word is bad. So let's see, we are going to insert B here, and the second character is A. So second, it's B's child is going to have A, and the third character is D. So from A there is another node which is again having 26 sized array, and we are going to insert D in it. So let's say D is the fourth character, so it is going to be somewhere here. So the first word is added. If suppose the second word is bag, then B is there, A is there, and the third character is G. We have to insert G. So G will be the child of A. So from here we will have one more array which is again of size 26. In that we will be inserting G somewhere in its position. So yes, we have covered both the words bad and bag. Same goes with max. So first character is yum. So this is going to be placed in somewhere in the position here in the very first array, which had B also, because they both are the first characters in the words. So now max is going to be inserted. So from M we're going to have one more array which is going to have space for all characters, and we're going to insert A, and A's child is going to be X, and A's child is also going to be D, which is for mad. So now D and then dot. So this is how we are going to construct our try, and each node will be having a marker is word to indicate whether it is the end of the word or not. So yes, this is how the complete data structure is going to be, which is pretty simple. So once you see the code, you're going to get it by visualizing it. So let's go to the code now. So yes, let's go to the first method. The first method is a place to declare our data structures. So as I said, we are going to have two items in a try node. The first item is going to be the array. Yes, as I said, we are going to have array of size 26, and a boolean variable is word, which is going to mark the end of the word. So that's it. Let's move on to the add function. So here's the code for add word function. So we are going to declare a try node, which is nothing but which is going to hold children of 26 characters or 26 try node, and the boolean word is word. Boolean character variable is word. So now we are going to take a word which is going to be inserted from the input, like add word bad is coming, then this word is going to be hit, and from the word we are going to iterate each character, and if the character is equal to null, then only we are going to put the character in the index. If not, if it is not null, which means prefix of that word is there already, with the first character is there already, we are going to simply insert the rest of the characters. So if it is equal to null, then we are going to insert it at the position. That is c minus a is nothing but we are converting that to an integer index and putting it in the try node. If not, if it is not null, then simply we are going to assign that as the current node so that the rest of the characters will be inserted as part of its children. And finally, after iterating all the characters and inserting all the characters of the word, at the last word we are going to insert is word is equal to true. So yes, this is a simpler function. Once you imagine what we have pictured, you will understand it very well. So let's move on to search method. So here comes the search method. In search method, we are going to call a helper method, which is nothing but a recursive function to search for the word in the data structure. So it simply calls the complete, it sends the parameter as the character array of the search word, and then 0 is nothing but the starting index of the word. So it will iterate till the size of the word, because if we want to find a word of size 3, then it is going to iterate or call its function thrice to identify the word, and root is nothing but the very first character of the word or the root node. Then here comes the match method, which is helping us to match and find the given word recursively. So let's first go to this function directly, this line directly. So which is a straightforward recursive method, which is gonna check if the character, the children of that node at that position is not is equal to null, which means if we have to search for the word pad and there is no pad in the data structure, there is no p in the data structure, then which has to directly return false. That is what we are going to first check, if the node dot children is equal to the character or not. If suppose there is a word that says dap, but the word pad is not there, we have to check for pad. In that case, p is there in the data structure, but that is not the immediate children we are searching for. So hope you understand. It has to be at that height of the tree so that it is at the correct position. So now if it is not null, we are going to search for the next character, that is the character at index +1 and in its children. So now the node is first character, then its children would be the characters at the level 2. So it keep going on and matching it, and finally we'll be returning true or false based on the search. So this is the straightforward method if the given words are characters. If not, if it is a dot, then we are going to take all possible children at that level, and from there we are going to explore its children by calling everything recursively, and then if everything matches, then we are going to return true. And where we are going to give the go to return true, because here is the check. If k is equal to length of the given characters, which is nothing but we reach the end of the word to the last character, and the word is true, then we are returning true. If not, its word is false, then we are returning false. Yes, that's it. And this is the overall code of this problem. Hope I explained it clearly. So let's run and try. Yes, let's submit. Yes, the solution has been accepted and it runs in 76 milliseconds. So thanks for watching the video. Hope you like this video. If you like this video, hit like, subscribe, and let me know in comments. Thank you.